The Display, a tale of 4 generations. And the speakers are Peter Stuge and Felix Niklas. And give a big applause. Thank you.
Thank you. Thanks for having us. I'm Felix, and this is Peter. Hi. So, yeah, we're going to tell you 4 tales about the display. The beginning of the display was that one of our club members bought it on eBay, and we didn't really know what it was used for before. It was done by a metalworks company who had an electric department that built the electrics for this, and the metal shop, they built the hardware around it, the nice frame. And they sold it off, I think, because it didn't work out for them. Okay. So we got it on eBay, and it was, in the beginning, very, very slow. At first, I wanted to show the outline. This is how it looks inside of our club. It's mounted on the wall. So we're going to talk about the hardware, about the first until the 4th current generation. We're going to talk about some software work that went into it, font and tethering. Then about the APIs that we have, the UDP and WebSockets, and then some fun applications that we ran on it. Peter, you want to start with the hardware?
So hardware. Yeah, first generation was delivered with a 6502 somehow controller board. I wasn't there when that was being used, but some people managed to get it working and send some serial protocol commands to the controller, and were able to watch the characters be drawn on the display. It was, as Felix said, really, really slow. So this is made up of a whole bunch of these LED matrix or LED modules, 8x8 little LEDs. No slides? Ah, there we go. Thank you.
So let's get back. This is the controller.
This is the controller, right, the 6502. And these are the 8x8 LED modules that are on this display. And in total, there are 20 rows going down and 56 columns. So that of these LED modules, 8x8, in total, that's 1,120 LED modules, and with 8x8, that gets us 71,000 and some LEDs. So it's a 71K display. So that was the first generation, and we got to know the hardware a bit, and some people in the Berlin CCC, they made a new controller for this, because the 6502 wasn't a lot of fun and was, as we said, quite slow. And of course it wasn't on the network, so we needed to get on the network. Second generation was an Atmel X Mega. I'm afraid we don't have any photos of it. No. Yeah. At this time, there was also the beginning of a protocol designed for sending information to the display. It consists of UDP packets that have a 10-byte header containing 5 16-bit words in network byte order. That's important to us. First one is the command. We'll get into those in a little bit. And then there are 4 parameters that may or may not contain some value. If they're not used, or if one parameter is not used, then the value is just 0. After these 10 bytes, there may or may not be some data payload also in the UDP packet. These are the commands. In the beginning, or the first commands that were implemented, I'm sure there are a few. So you see there are some gaps. I don't know actually what the commands there were or the numbers there were anymore. But clear, obviously clear screen text, sending code page 437 text because that's a fun encoding. And then we had some brightness commands. These LED modules, the 8x8 modules, it was mentioned on the slide. Behind each of them is a Maxim Max 7219 LED driver made for this kind of matrix, LED matrix display. And in this LED driver, there's a digital register for setting the brightness. And we exposed that using some commands.
Let's show a demo of that. This is a demo one of the members of the club did to test just changing the brightness. Since we can only do 8x8 brightness changes, he still found a way to do a nice application of that, because for movies, obviously, it doesn't really work to do grayscale or like color tones on 8x8 pixels. But in the end, he used 8x8 graphics to do this nice depth map.
Yeah, so this, to explain what we're seeing here, the whole display is filled with plus signs. So every one of these 8x8 modules is showing a plus sign. And the only thing that is changing is the brightness value or the light intensity of these modules. And that makes for a nice, even low resolution effect on the low resolution display.
Let's go back.
Going back to commands, yeah. All right, so that was character brightness, setting it on individual modules, and brightness for the full screen. In one command, just a reset command, because that helps sometimes. Then we had a fade experiment where a graphics kernel runs over the display and sort of reduces intensity, which looks like a fade. It didn't get used very much. And the main command, the most important thing, yeah, the most important new feature in the in our development was to support bitmap transfer, so that this display could also show arbitrary graphics. And the very first command, because it's easier, received the bitmap data in a way that fits how the hardware was built. And that's not really so intuitive or so convenient for software developers, it turns out. Is that here, or is it, yeah, pixel data in a vertical layout? So the bitmap data was sent with each byte being 8 pixels high or tall instead of 8 pixels across, which is what we usually deal with in software. So still, we could do bitmap. We could display bitmaps. That was a lot of fun and a good start. Right, and then we of course we want to go fast, right? So we found out actually the hardware, the factory hardware is the construction is quite limited or quite slow. Because not only because the 6502 is a relatively slow machine, but also because of how the whole data transfer was implemented in this display. So as the arrow shows here, the 6502 processor would address every single one of these 1,120 LED modules at a time and in sequence, meaning that the other 1,119 LED modules were just not doing anything most of the time, right? There's only one module receiving data. So this was changed in hardware generation 2.5, where so actually we weren't using the 6502 controller then anymore, but anyway, it's just representative here. The main controller, the master controller, sends data to these new row controllers that were designed in CCCB by some members, and they have a distributed video memory. So each row has a video memory for the contents that is there, and also parallelization. The master controller sends data to all the row controllers and only to the row controllers, and the row controllers then take care of sending data out into the LED modules or the LED driver chips. That is what it looks like.
I have two pictures.
there's a bug in the hardware that we fixed. Yeah. But that was good. That got us some more frame rate in the bitmap transfer. And then then that wasn't enough. It was still too slow for us. So we then made an experiment with a microcontroller that is a bit more powerful, well, fair bit more powerful than the Xmega. A Cortex M3 ARM microcontroller, I believe 96 megahertz. And the thing about these particular ones is that they had Ethernet MAC and PHY built into the Cortex M3 microcontroller, which was quite unusual, but very suitable for our project. So
we still had the main problem that the graphics, the bitmaps would have to be in this weird order, going up and down instead of how we're used to it from left to right. So.
Yeah, so this is within one row. You would have to send these vertical bytes, and that wasn't at all fun. And we decided to solve that in generation 3. We implemented a few new commands, two new bitmap transfer commands to support just the regular linear bitmap transfer that is used also in a regular PC or computer to represent bitmap data, where you send the pixels after each other horizontally, and then you move to the next scan line and so on. So there's
more processing power, and we use that power to make it easier for developers.
And also this ARM architecture had some nice instructions to do this bit transformation, like to rotate 8 by 8 bits was fun and easy. And this the 2.5G new row controllers, they jumping back a bit, they made some optimizations as well to sort of reduce the data transfer that needed to go into the rows, because we had some flickering and we didn't have completely stable data transfer. But reducing the throughput helped with that. That allowed us to still update a lot of changing information, but areas that were all the same, they didn't get updated at all. And to save power also, if one of these 8x8 modules had no LEDs on, then this particular Maxim chip would be set to power save mode. So one also wanted to improve efficiency and reduce power consumption. When we started out with the Gen 1 hardware, somehow we have some measurements. We believe that we measured it to be over 1 kilowatt with all LEDs on. And we've improved that with each hardware generation, and we'll come back to power in a little bit.
But it wasn't perfect yet. There was something with the Ethernet, I remember.
Yeah, so this bitmap linear command and the linear windowed command, where you can only update, you cannot choose to update only a portion of the screen. We had the issues with this Cortex M3 that it did have a built-in Ethernet MAC and PHY. So network connectivity was easy, and there was example code for an IP stack, and all was good. But unfortunately, the hardware only had 2 kilobytes of packet buffer memory. So if we take these 71,000 pixels and we want to, or bits, and we want to send those in one packet, we have a bit of a problem, because that's some 9 kilobytes of data. And with this microcontroller only having 2 kilobytes of packet buffer, some packets are going to get lost. So that was a bad scene, and we worked around it by, instead of then sending one big UDP packet with the full image data, we would manually do what the IP stack does. So we send one UDP packet with 9 kilobytes of data. The network stack divides this up because the network can't transfer that big packets, and it splits that up into 6 or 7 packets of 1,500 bytes or whatever the MTU is. Sends that out to the display, but the display only receives the first and the third and the fifth, because in between it's busy copying the packet that it just received into the display memory. So what we did as a workaround in the first, to overcome this at first, was we did this splitting the video frame, or I revealed the secret now, splitting the image frame into several packets already on the sending side, not in the IP stack or the network stack, but actually in the application. So we made a video or image transfer application, and there we cut up the image in little packets, and we built in an artificial delay between the packets, and that really hurt. That was painful. We didn't like that at all. Not a nice.
Because you have to understand, the goal always was to get more FPS.
Of course, we want to make it go fast, and we want to be able to play video on the thing. That was always the goal. The second generation had a few FPS, like 2 or 3 or so, with the bitmap transfer commands, and with the third generation, we were able to get it up to some 9, 10, maybe 12 FPS on a good day. But we weren't happy because that didn't look so nice still. So then we took out the sledgehammer, and we decided we'd try to use a BeagleBone Black, because it has the PRU, which is the programmable real-time unit. So the BeagleBone Black, many people know as a Linux board, similar to another fruity board that I won't mention. And it is a Linux board. It's a nice, roughly gigahertz system on a chip. But inside of this, there are also 2 coprocessor cores, so 200 megahertz little coprocessors that are completely separate from the ARM running the Linux system. And you can write little program snippets for these, and they run quite fast, 200 megahertz. And they can do I/O, single cycle I/O, GPIO, well, writing and reading. And that we figured would be a very good way to increase the performance, the last bit that we needed. And so we'd taken several steps. We'd already optimized the data transfer going over this the ribbon cable that you can maybe see through the front of the display. It used to be serial with the very first hardware. With the second generation hardware, it was still serial. With the 2.5, we changed it to parallel, so 1 byte would be transferred at a time instead of just 1 bit. And the row controllers would then take care of sending that data out serially, 1 bit at a time, because they have time while the other row controllers get their new data. And with the BeagleBone Black, we continued that, so we write some PRU firmware to talk to the row controllers and send them out the data. The PRU has a shared memory, so the Linux system just receives bitmap packets, or really command packets, looks at the command and does whatever is necessary and saves the bitmap data into this shared memory. Does nothing else, does only that in a loop. The PRU is running independently a firmware that takes the bitmap data out of the shared memory and sends it out the bus to the row controllers. So even more parallelization. And with this, we were able to go all the way up to 40 FPS. So that's, yeah, mission accomplished somehow.
Let's show some pictures of the insides.
Right, so this is the current state of things. We have the BeagleBone Black up top left with a cape on a breadboard with, I think there's some level shifters and maybe some I/O buffers. I don't remember anymore exactly what's all on there. But yeah, to drive drive the bus going down. And you can also see the power supply here. This is quite a small power supply. It's not enough for the whole display. It's only powering the BeagleBone Black. And this is part of the other, well, the real power supply, let's say, for the LEDs. Is there one more?
There's two of those.
Yeah, there are two, exactly.
But we didn't catch that on.
Right, the two of these power supplies are needed to drive all of the LEDs. I think they are, I don't remember anymore. I think they're 500 watts each, but we don't actually need that much. And we have two because there wasn't a single one that was high capacity enough and fanless.
But they've been in the hardware since the beginning. We didn't do this, right?
We did this. We mounted these power supplies. There were other power supplies before that were really inefficient. Okay. So switch mode power supplies from the 1990s were replaced with some modern switched.
And who did that nice wiring?
Ah, we did that in CCCB. Yeah.
Okay.
Yeah, nice. the red and black but these copper bars and the fuses, they were already there, so they are a factory. And this little board in the center there is an AD converter to monitor the voltage output of these power supplies, because we wanted to see, okay, when we switch on and off all of the 70,000 LEDs at a time, do the power supplies actually keep up with that? And yes, indeed, they do. It's a stable 5 volt. Yeah.
This is the bottom right corner where there's the power connection and the Ethernet connector, and there's a nice engraving showing our logo.
Yeah, we had to tag it.
Okay, so let's go over to software. Like, as you might already feel, I don't know that much about the hardware, but it was always a pleasure being in the CCC and getting hearing about seeing all that's being done by the different members of the club. Everybody's just pouring their heart out with what they were good in. And I do web development, so I only was able to do stuff after they delivered a web server on it and gave me WebSocket, which we will be talking about soon. First, let's quickly talk about the font. So the font system is a CP437. I'm too young to really know this, I think. I have this feeling. But you might also know this from the boot screen, because that's the same system being used there.
And MS-DOS.
And MS-DOS.
MS-DOS used this,
I know that.
Yeah.
So there's fonts out there, obviously. Why would we need our own? Because we have our own. One member built one. The problem is, we have 8x8 pixel modules, right? And there's 8x8 fonts. That's one of the standards. There's two different types. One is higher. It's 8x16 or something. That obviously wouldn't fit, but 8x8 would fit perfectly. But there's a problem. Our modules are one next to each other. And when you put text on there, there's no space in between. So that was the need that we needed to solve, that we have to have a gap. So in the end, a 7x7 pixel version of this very basic font was created, and this is the bitmap of it. This is the basic texture set that's in there right now, and I don't know if you see it on the screen, but there's a light gray area on the right of the 7x7 areas. This is the gap next to it. And Marco, who was working on this, he created the font, I think, in Windows.
MS Paint?
MS Paint,
he said, yeah.
Like in a virtual machine, now in Wine, I think, because he said this is still the best thing if you want a pixel. GIMP is not good enough for that. And then he created some scripts around to export it and to, on the one hand, create a C header that is being used on the BeagleBone. And he also outputted a web font that we were able to then use in the web editor, the web interface of the display, to see almost the same directly on your browser. And then the next big thinking was put into dithering. I don't know if you know the concept, but I mean, let's say we have an image frame and it's color. Obviously, we don't have color in there. So we need to make it into something, oh, step 1.24. We need to first convert it to black and white. But then again, I told you before about the brightness. We can only change the brightness in an 8x8 area. So we couldn't do like gray in there, right? We can only do green or black or nothing. So you need dithering, which is a technique to create that effect by just using space, by just using less white, well, in this case, green dots. It's the same technique, almost the same that printers are using, because they also only can print black and not black. So let's zoom in a bit to maybe see this a bit more. This is like a dithered image. And Marco put a lot of love in this. He even built like his own Love 2D, like a Lua application to test a lot of different dithering algorithms. There's Floyd Steinberg, which is a very basic one. But he quickly saw that this is not good enough. It's not fitting the high quality standard that he was aiming for. And so this was the application he built, where in the top left corner is the original image. It's actually in color, and there were different ones for testing. And then he could compare two different dithering algorithms in the middle and bottom picture. And in the end, he settled for, I don't have the name here, it's starting with O, and I think it's a Russian name, O something something, as a base algorithm. And then he added also some more pre-processing to improve the results further. He does some blurring in the beginning, because in the end, you won't see all the details with the dithering. So he blurs out, like the blurring will remove the details that won't be shown anyway. And then he does some sharpening afterwards to make those features that are going to be shown a bit sharper. And you see it in the bottom left. It's not a really good representation because it's scaled, and when you scale dithered stuff, then it's bad, but you see the result on the screen itself. Packages or
UDP packets, yeah. So 9 kilobyte bitmap frames. Maybe I said this already. Let's see what's the next. The UDP.
We have to speed up a bit as well. So maybe
the most
UDP
packet
thing was WebSockets from my point of view, because I never touched UDP before. And with WebSockets, I was suddenly able to send pixels to this display in the browser using JavaScript. The WebSocket API is not the full API. It's not the same as the UDP API. It's just for sending pixels. So I was mostly working with it, having a canvas, and then just sending the canvas data, the pure pixel data, directly to the display. There's a simple demo application showing the WebSocket implementation, or how to send stuff there. I don't know if it's big enough to see, but in the end, WebSockets it's a two-way communication based on TCP actually for the web to send stuff somewhere. And you just build up the connection, say that you're going to send array buffer data, and you grab the pixels from the canvas. At first, I did that before. I drew a rectangle on the canvas in this case, and then go through all the pixels, pack it up to bytes, and just send it out. And it was actually quite simple to build applications with that.
It's a very simple protocol, but it worked fine.
So let's talk about applications in the CCC B, what we did with it. So the basic one is a welcome screen. Since it's mounted on the wall, usually whenever we have open days, it's on, and this is what it's showing. It's not always on, obviously, but usually this is also the boot screen. One of the first, one of the early implementations was when we didn't have the bitmap yet, I think. Correct me if I'm wrong. Then the first movie was an ASCII Star Wars movie. There's apparently something where you can tailor it in and it just sends you this data. It was nice for a beginning. But then obviously, which you already see live, video. Mark built a nice GStreamer plugin so that you can that takes care of all that dithering, all the pre-processing we were talking about for you. So you could just send your movie that way, and it would correctly send it to the server. There's one small thing we didn't talk about in between. At one point, we optimized also the data load by compressing it as well, right?
That's true. Yes.
I don't know if it was between third or fourth generation.
That was added into Gen 4, into the fourth generation. So these bitmap commands, well, one of them particularly only uses two of the 4 parameters in the UDP protocol, and then we introduced some subcommands supporting different compression algorithms there. Dennis was busy quite some time working through all the different compression algorithms that he could find, and settled in the end on Z standard for decompression speed in particular, but still a reasonable compression rate.
And also something you might think about is the lines in between. Also, one of the steps of the GStream plugin is to cut out some pixels so that it doesn't look stretched in the end.
So the way that works, the GStreamer plugin says to GStreamer, please deliver grayscale images to me that have more pixels than fit on the display. And in these bitmap transfer commands, then the gaps where the metal is are copied over. So it's a little bit of, it's unfortunately not zero copy, but it's not enough data to be a problem, and it looks a lot better than just asking for the exact pixel resolution of the display. Then the image is compressed together and not really recognizable.
And then when you connect to the API to the IP of the display, you would see this web interface. Just had a basic text mode where you can, or it has a basic text mode where you can just type stuff on the screen. And there's a small canvas drawing application in there as well to do some drawing on screen. Then one of the fun things was also a Bitcoin info screen somewhere in between with live updates. Pixel flight schedule.
I like this one a lot. And there was also one for the, is that one up next? For the,
yeah, it's the next one.
Yeah. Yes, this one is really good. So on the open nights, there's the Friedrichstraße station right nearby the club, and towards the end of the evening, because it's weekday, the trains stop running at some time, and it's very nice to have this like sort of countdown when you have to leave to catch the last train.
Nice catch of time, I just realized. 2, 3, 4, 2.
Not bad, not bad.
And also a really fun project was a multiplayer tank game where you would use your phone or your laptop. You would connect to the IP where you would get a controller in your browser. And on the phone you could, for example, also use your touch movements to steer your tank and then shoot each other in this multiplayer game. And the display was the map. And then last up, there was a nice demo application for the iPhone where you would just stream the camera to the display. And
all right, so
that's
credits. Thanks to everybody who helped work on this project. Everybody who did work on the project. It wasn't just me and Felix, but a whole bunch of people at CCCB, and I always had a lot of fun working together on this thing, and I sort of missed that a little bit. It's been a while since somebody did something with it, right? And yeah, let's hope that changes.
I gotta say, I don't miss it because it's always so dangerous when they are handling it with 150 kilos in the club. It's really, really weird. So, thanks to you two for now. Do we have questions? Sehe ich ein weißes Licht? Dann bitte mal ins Internet.
Hi. You mentioned that the modules can be dimmed. That's where you did your first animation with. Does the dithering algorithm also use the dimming of a module, or is it just let on or off?
The dithering, as far as I know, the dithering doesn't use the intensity, light intensity, because that's only possible to be controlled in 8x8. And I mean, you could, I think it was actually attempted, but it didn't really look great because the pixels are, well, much smaller than the area that you can control the intensity of, and it didn't look so nice. So
you would also have to send several packages, like one for the dimming, one for the pixels again.
Right, two different commands. I mean, we could have added a command that to do both, but it didn't look so great. Yeah.
Okay, we have another question here in the front, please.
Thanks for your talk. Maybe you have other ideas of upgrading other old, nice devices. Can you share?
Other ideas of upgrading old devices? Well, when you have a device?
I mean, the screen is, so you upgraded it, it's now much better than the original one.
Yes.
And maybe you have ideas for more projects.
If we have some future projects, you mean?
Right.
Something like this? Yeah, okay. At the moment, no, unfortunately. I mean, so there's been some work on other display technology, some flip dot projects we've done, but not so much in the club, not as a club project, more that the same people who worked on this also did some flip dot hacking, but yeah, not at the moment.
If you have suggestions, please just send a mail or, yeah, do it yourself.
You can go on eBay, buy something, send it our way.
But don't send us your waste, right? Don't send us old waste. And we're not going to do this. Or do we? No, we don't.
No.
We have one more question in the back, and that's the last question, please.
Or no more question.
No question? You're just standing there. Perfect. Can happen. Okay, then thank you so much, and give a big applause to our speakers, Peter and Felix.
Thank you.
Thanks a lot for having us.